we've been talking about ideal gases, and ideal gases are defined with the ideal gas law, PV equals nRT. So normally when we're talking about ideal gases, we don't differentiate between which gas is what. They all behave the same. They're all ideal gases. However, we do live in a real world, and in our real world, we are surrounded by gases, and the gas that we're surrounded by happens to be a mixture. So in order to define that mixture of, for example, air, we need to be able to define the amounts of the different pure substances that are in air. In other words, the concentration of the gas or gas concentration. How do we do that? Well, we define gas concentration normally in terms of percentages, parts per 100, parts per million, or parts per billion. So let's take a specific example, air. Normally for air, if we want to talk about, well, how much oxygen is in air, for example, we use the unit percent. There's about 21%, 21 parts of oxygen per 100 parts of air. And when we talk about the parts, a lot of times we call them particles. 21 particles of oxygen per 100 particles of air. And the particle is defined as an atom, an ion, or a molecule. So 21 molecules of oxygen per 100 parts of air, whatever those particles may be. Now, when we're talking about carbon monoxide, we typically don't use the percent unit. Instead, if we're talking about carbon monoxide, for example, in downtown Austin, the concentration of carbon monoxide on the street might be 0.0009%. So normally when we're talking about the concentrations of very tiny amounts of pollutants, we use different units that conceptually make more sense. Instead, when we're talking about how much carbon monoxide is in the air in downtown Austin, we would say 9 parts per million. As it turns out, 0.0009% is the same as 9 parts per million. That's why we use the different numbers. It just makes more sense.